For the next topic, pH and acid and base solutions, what I've done is I've uploaded this handout that has everything already filled in for you. So again, just like I did with chemical equilibrium, kind of want to just talk you through it, and this will serve as mainly the lecture over this material. This is what we would have done yesterday on Thursday. So that way then when we meet again on Tuesday, I can go ahead and begin the next topic to kind of help us to get caught up or stay somewhat on track, but at the same time then I'll give you a chance to ask some questions. But picking up with what we left off with, talking about chemical equilibrium, we are talking about an electrolyte that is not a strong one. So as I have listed here, Roman numeral 1, or topic number 1 here, is that we have to remember probably one of the most important things that we do in the understanding of chemical reactions is to think about what happens to chemical species in aqueous solutions. So the whole idea that you have some substances that are going to be strong electrolytes, that would be strong acids, strong bases, make that a B, and then that you would have soluble salts. Those are the three classifications or three types of substances that would be strong electrolytes. You would have then as weak electrolytes, those that only dissociate or ionize partially, because it's actually then a reversible reaction. It's an equilibrium reaction, forward and reverse. Those are going to be for our substances that are going to be weak acids and weak bases, and those are the only two types that you can have. Well, at least so far, as we've discussed, those are the only two types of electrolytes or substances that you can have because they'll engage in a weak conductivity with the little conductivity tester, and that's because you only have some ions in solution. It's the presence of the reverse reaction then that makes it go back into the neutral molecule. Third, you have the non-electrolytes, and we're not going to talk about those now because if they're non-electrolytes, that means that they undergo no kind of a transformation into ions in solution, any kind of an ionization or dissociation process, so therefore no discussion. There's not going to be that much interesting chemistry. It's sludge that sinks to the bottom of the test tube and doesn't do anything. Okay, so what we're going to do first is look at specifically then for acids and bases. So that's going to be the crux of this topic for this part of our discussion of equilibrium chemistry is what about acids and bases, and how do you tell to what degree of ionization that particular acid would be, because you can have strong acids or you could have weak acids. You only have 7, remember? There's only 7 acids that are considered strong acids, and then strong bases, they're just those that are the alkali metal family. So if you had like lithium hydroxide or potassium hydroxide, and then calcium, strontium, and barium out of the hydroxides out of group 2. And then the rest of any kind of a base that would be either a Bronsted-Lowry base or a Arrhenius base, those that you can see physically, the OH in the formula, the hydroxide anion. Those guys are going to dissociate 100%. And so we want to know, okay, well, how could you tell just to what degree they do ionize? Is it 100% or is it a little bit less? Remember when we did molality, you can have things that aren't perfect 100% ionization, that maybe you would not fully get all of the ions in solution. And then definitely for the weak electrolytes, those weak acids, so all the other gazillions that are not those 7 strong acids and the gazillions of bases, to what degree of ionization do you have? Well, that's where the idea of pH comes in, is that it's a nice way, a technique that's in the laboratory in order to measure just how acidic, or you could do analogously the basicity of a solution, to tell you what that degree of ionization is. So first we'll just take the strong electrolytes, and then that'll take 2 seconds, then get into really where all the interesting chemistry is, which is going to be the weak electrolytes. So calculating the concentrations of the ions in solution, in other words, seeing, okay, this is what they are going to dissociate into. So, for example, here's nitric acid. Remember, that's one of the 7 of the strong ones, so you've got to have those down pat if you don't remember them from Chem 1. They're on that list, the aqueous electrolyte handout. So you got HCl, HBr, HI, H2SO4, HNO3, HClO3, HClO4. Got the 7 of them, okay? HNO3 is one of those. All right, so the trick of what we're trying to do here is if I had then a solution of nitric acid that was prepared with molarity of 0.050, okay, that of course then is going to be aqueous. what would be then the concentration of the ions when the ionization process takes place? Okay, remember essentially what's happening here is that you have the splitting of the cation and the anion, so it's the H plus and the NO3 minus. But remember, there's really no such thing as H plus in solution, because then the H plus ions, that's just a proton, right, that it reacts with H2O, and so you get the hydronium ion. And then of course you get the NO3, which then, if you recall, that's the conjugate base. That's the conjugate base ion then from the HNO3. Notice then that if my concentration of nitric acid begins being prepared as 0.050, well, then the concentration of both of those two resulting ions in solution is going to be just in a 1-to-1 stoichiometry. And it's only got a forward arrow. Note, it's only got the forward arrow here because he is one of those 7. And so at least on paper, for sure, we're going to say that he has 100% ionization. Okay, practically speaking, in the laboratory, that puppy is 100% ionization as well. So we're good to go. All right, here's a base. What if I had then 0.020 molar strontium hydroxide? Okay, kind of shorten it up and not have to put the aqueous part in and just say, hey, we're dissolving the solid in water. Bases, the hydroxides typically are solids at room temperature. They're ionic compounds. Nitric acid, that's all covalent, right? Everybody's a nonmetal in hydrogen. So a lot of those guys are going to be more in terms of hydrogen bonding. They'll be more like liquids and gases, some of them per se. But strontium hydroxide, you got a metal there, so ionic compound. Ionic compounds are solids at room temperature. Dissolve him in water. Okay, well, strontium hydroxide, he's one of the 6 main ones that are the strong bases. And so then here's your strontium ion, 2+ charge. And then take note, just like we did in our ionic equations a while back, 2 units back or 2 topics back, that you then are going to have 2 of the hydroxide ions. So remember doing that's a Van Hoff factor, I equals 3. You had 3 total ions produced in solution. Notice that you're going to do the stoichiometric calculation that the strontium then is in 1-to-1 ratio, so the concentration of the strontium ions is 0.020. Not really worried about him right now. The main one here then is what is pertaining to being a base, that the concentration then of the hydroxide ions is going to be 0.040, just doing a 1-to-2 ratio, because you had 2 hydroxides for every 1 mole of strontium hydroxide. Now, why is this important? Well, because if you know the concentration of the hydronium or you know the concentration of the hydroxides, that's what's related to this thing called pH. That's going to tell us then the level of acidity of a solution. Now, before we get into that though, let's talk about then those 2 ions in solution. If you have a hydronium ion and a hydroxide ion, lo and behold, we're going to take into consideration that water undergoes what's called auto-ionization. In other words, this is a Bronsted-Lowry reaction. Somebody's an acid, somebody's a base, somebody is going to be donating a proton to the base, thereby then making a conjugate acid, and that acid, upon losing that proton then, is going to turn into a conjugate base. It's probably only about 1 out of every 2 billion molecules of water or so that actually undergo this reaction, and you'll see that it is indeed a reversible. It's an equilibrium process. But even in just a simple glass of water, if you had 8 ounces, forgive me for using the English system, you have 500 milliliters of water or something. Even in that small quantity of water, 2 out of every billion or so, maybe or so, or 1 out of every 2 billion or so, they're going to be a sufficient number of those water molecules that can actually act as a Bronsted-Lowry acid and base, giving you then some additional hydronium and hydroxide ions in solution. Well, so what's essentially going to be happening then is, even if you have an acid like HNO3 dissolved in water, or HCl, or HBr, or anything else, you're always going to be monitoring the level of hydronium ion in solution as being the strongest possible acid. We had talked about this in another unit before as well. And then likewise, with hydroxide, that's considered to be the strongest base that could ever exist in solution, just literally the hydroxide ion, because of this effect, or it's called the leveling effect, a vocabulary term I've used in the past. So the strongest possible acid in aqueous solution is the hydronium ion, and then same thing for the base. It'd be the hydroxide ion. Okay, well, if you look at that reversible reaction, you'll see that I've got 2 species that are aqueous, those are the products, and I've got 2 species then that are reactants, and they're liquids. If I were to write the equilibrium constant, I'd put my products over my reactants, and then guess what? Remember in our heterogeneous equilibria, the last thing in the last video, the previous video? If it's a liquid, you just take that to be an activity, aka molarity, of 1, and so those guys completely drop out of the equilibrium expression. That leaves you with a concentration equilibrium constant then that will only have the concentrations or the molarities of the two products. So this is called the autoionization, or the reaction is called the autoionization of water. The equilibrium constant then is labeled the equilibrium constant or the water constant. And so we now have a designation specifically for that that we call the Kw. You want to memorize this value for sure. You don't have to memorize a lot of equilibrium constants, but this is going to be one of them that you do have to memorize. I should say you really don't have to memorize any, but this one you will because you're going to use it so often. What this depicts for us then is that in aqueous solution, the level or the amount, the concentration of the hydronium ion then is going to be inversely proportional to the hydroxide. It's sort of like having x squared equals 1 times 10 to the negative 14th. So when one goes up, the other one's going to go down. Okay, this is for room temperature, standard conditions, 25 degrees Celsius. If the two concentrations are equal to one another, then notice how then the relationship between 10 to the minus 14th and then just simply 10 to the minus 7th, okay? Where this is heading is that you may remember from biology that a neutral pH was 7, and that you may remember that the pH scale went from 0 to 14, Therefore, this is really where that information on the pH scale that you've probably learned back from elementary school, this is where this is all coming from. You would have a completely neutral solution, right, if the amount of hydronium and hydroxide were the same. Okay, so we can use that relationship very easily then to calculate the concentrations of hydronium and hydroxide in any solution of an acid or a base, because they're related to one another by the Kw, that we're in an aqueous environment. So, for example, here I've got concentration, I just made these guys up. Here's HCl, we'll make him just a 0.050, I've got that on the brain, 0.050 molar. Okay, so 1-to-1 concentration, or I'm sorry, 1-to-1 molar ratio, okay. So the hydrogen ion concentration, you can either write H+, we really know that that's hydronium, okay. We kind of get lazy and we just write H+, so it's okay, but we, just keep tucking in the back of your mind, it's really hydronium ion there. That's going to also be then 0.050. So that's my hydronium concentration. Okay, well frequently what we'll do is ask you to find out what are both of the concentrations of the hydronium and the hydroxide. So it's just a matter then of knowing that equilibrium expression and constant value of 10 to the minus 14th, plug in the hydronium concentration, solve for X, or in other words solving for the the hydroxide concentration, and so you can easily just use that relationship. Given one, you can always find the other one. Okay, now it gets a little bit more interesting then if you are going to try to find out then to what level of acidity is that solution, okay? So once you know the hydronium concentration, then you can find the pH. So here's the schematic of what the pH scale is really based on. It's powers of 10. So hence, it's a logarithmic scale. People might say, okay, the pH of the human blood averages somewhere between, say, like 7.2 and 7.4. And so then when a person's having a heart attack, their pH of their blood actually goes down, okay? We could talk a lot about that. It'd be an interesting discussion. Talk about that in anatomy and physiology or something. pH goes down, becomes more acidic, and then besides the heart kinking out on us, then it's really that pH that does a lot of the damage to the muscle tissue when it goes to be too acidic. Well, so people might say, oh, well, hey, if the pH of the blood's only changing from, say, like 7 to 6, well, that's only one, unit away, but it's really a factor of 10. It'd be like saying that the molarity had jumped by a factor of 10 or had decreased by a factor of 10. So it's really, really a significant thing. Okay, anyways, pH. Good little trivia. The P really stands for the word power of the hydronium. But the P of then something, pH, is literally then just the calculation that you're taking the negative log of whatever that is. So pH then is going to be the negative log of the hydrogen or hydronium concentration. A lot of biology people, they'll prepare like buffer solutions or protein solutions where they need to prepare things according to the pOH. So that's just analogously then taking the negative log of the hydroxide ion concentration, okay? They would be reverses of one another, right? Okay, we typically think of the pH scale. I've got the little picture here pasted for you, okay? pH scale going from 0 to 14. Here it's got then approximately the relationship between then what would the hydronium concentrations be for all those different things. They're just the powers of 10. So 10 to the negative 1, okay, well that's 0.1. 10 to the negative 2, that's 1/100th. 10 to the negative 3, and how that when you take the logarithm then, it's taking the logarithm then and the negative logarithm of it that turns it into the nice integer, 1, 2, 3. And you can have decimal places as well. And then see, there's your neutral idea. Well, so if you wanted to do the pOH, you could have a pOH scale. It would just be the opposite. Well, then you would have, these are the basic conditions, and then down here would be your acidic conditions, or another, or higher on the scale, okay? They would just be opposites of one another, so you can do them complementary. Why does that work out? Because remember, hydronium times hydroxide is 1 times 10 to the minus 14th. When you take the negative logs, I'll leave you to do the arithmetic. When you take the negative log expressions and put those together, that's pH and pOH. When you take the negative log of 1 times 10 to the negative 14, it comes out to be 14. That's a handy dandy relationship as well. So you do have to memorize the formula for pH, and then just remember that's an analogous for the pOH. But that idea that the pH value then plus the pOH value summing to 14 is a very quick and powerful relationship that comes in handy when solving calculations. Okay, now formula number 5 then, and then the analogous one for the OH, okay? What I've done is I just took formulas 2 and 3 and solved for the hydronium concentration. So I took the anti-log or the inverse log. So there again, this is a handy dandy formula to memorize or to work out the algebra on your own. Taking the inverse log is that 10 to the negative of whatever the pH is. That'll give you back the hydronium concentration. 10 to the negative of whatever the pOH value was. That can give you back then whatever your hydroxide ion concentration is. We will then use also, at the appropriate times, formula number expressions number 6 and 7. The P of anything is you take the negative log of whatever that is. So we'll have something called the pKa. K standing for, again, capital K, that's equilibrium constant. Little a is going to stand for acid. Little b is going to stand for base. In other words, if you had an equilibrium constant, okay, so now we're talking about weak electrolytes, not the strong acids, not the strong bases. This would be for weak guys, that there will be a reversible reaction, that there will be an equilibrium constant. You could find the negative log of that. That's called the pK, okay? So you'd have a pKa and a pKb. We'll use those after a while. And then, again, because there's this relationship, this inverse relationship between the hydronium and hydroxides, another interesting expression then, they go through and prove the algebra to you in the book. You can take the Ka times the Kb, and that's going to be equal to that Kw. So it's always a constant situation in these aqueous environments. It's always going to be coming out to be related to that Kw, that 1 times 10 to the minus 14th. Another reason why that's so important that you just memorize flat out. The Kw is 1.0 times 10 to the minus 14th. Okay, so of course expecting you to know the different regions of the pH scale and who's acidic and who's basic, okay? But more importantly then, probably so, is that we could then track the acidity of these solutions by doing the calculations. So again, just like I did with the equilibrium, kind of setting it up to, you know, if you're given this, then you're looking for this. That was how we did equilibrium constant calculations, and then do the reverse. If you're given the equilibrium constant, then go get the concentrations. Same thing here. What if you are trying to find the pH of a solution by being given the concentrations, or vice versa? What if I'm given the pH and then I'm trying to find then those concentrations? I want to take both scenarios. So first off, probably the easier of the two, what if you know the concentrations of the hydronium or the hydroxide? That problem that we just did where we were able to calculate. If you know the concentration of the acid or the base, you can go find the hydronium or the hydroxide ion concentration. All right, so it's a matter of just simply plugging and chugging. So yes, If I've got a hydronium concentration of 0.030, somehow I figured that out, maybe some, from the concentration of the acid or whatever, just plug that into your calculator, okay? Be careful. Depends on how your calculator does this. Sometimes you have to put the number into the calculator, then press the logarithm button. Make sure it's the log one. You need the common logarithm one, not natural log, okay? Press the log button, and then you would press the change of sign button. Most of them will write it like a plus minus key, okay? If you do these on the graphing calculators, you may remember if you did these in high school that you have to literally plug it in exactly as written, so that you'd plug in the negative sign first, then you'd hit your log button, and then it'll pop up a parenthesis for you, and then you put your concentration in, okay? Remember, you have to use the non-graphing calculator in class, but some of y'all might still use your graphing ones at home. I do too, but you may still want to use those. So anyways, however you plug that in, you'll get then your answer, and then note here, you may or may not remember from the absorbance experiment that you did back in Chem 1, that with logarithmic functions, that when you look at the number that you were plugging in, the measurement that you were plugging in, how many ever significant figures was in that number, you change that to then be that you will round off the logarithmic function, so that would be the pH, that you rounded off to the same number of decimal places. So your total sig figs probably will be different, okay? It doesn't have to be, but it could be, and probably will be. So like this here, 0.030 is only 2 sig figs. When I do the number rounded off to 2 decimal places, yes, my pH then ends up having 3 significant figures, but it's all because of this being a logarithmic function that you rounded off according to decimal places instead of sig figs. So 2 sig figs in your measurement gives you 2 decimal places in your final pH. Okay, so let's do another calculation. This one of the kind of reverse ones, okay? They give you the pH and then ask you to go get your hydronium concentration. Okay, so you can do this in a couple of different ways, right? I mean, you're just plugging and chugging, but you essentially plug in your pH, and then you're going to be solving for the hydronium concentration. So however you want to do the algebra, use that formula in that list of formulas that I gave you, how that you just take 10 to the negative value of the pH, and that's what gives you back that hydronium ion concentration. So really just a matter of knowing the expressions and then plugging the numbers in and then cranking it out in the calculator. For this 10 raised to the power, you probably want to use your caret button, or like just your power button, your y to the x power, or whatever. Or you can plug in negative 4.597 into the calculator and then do inverse log. Okay, inverse log, or maybe it's like your second function. When you look on your calculator, you probably would notice this, is that right up above the logarithm button on the calculator, it says 10 to the x. That's what doing the inverse log is that you're raising 10 to then whatever you've put in there. So you could punch in negative 0.4 or 4.597 and then hit inverse log, and it'll give you the concentration too. I would practice that, confirm. Do that calculation right now. Pause the video, do that calculation, confirm that you can get this to work on your calculator. And then when we meet again on Tuesday, holler at me. And if you got stuck on something, I'll help you. Okay? All right. So for the Strongs, it's just a simple matter of getting those hydrogen ion concentrations or hydroxide ion concentrations, because it's 100% ionization, so it's just the mole ratio, just stoichiometry, and then you plug it into the pH formulas or POH, whatever you want to do. Note, though, then, that if you have a weak electrolyte, so we'll concentrate on just weak acids, but there would be a similar discussion that you could do for the weak bases. Those that are not on that list of 7 strong acids, those that are not those 6 or so of the strong bases, the main ones, you have a weak acid, therefore there's going to be an equilibrium reaction, and therefore there's going to be an equilibrium constant. How the heck are we supposed to be able to figure out how many hydrogen ions end up getting formed in solution when we don't even know to what extent that particular acid is going to dissociate or ionize? Well, 2 things. One is, again, it's kind of the scenario is if you have the concentrations, you can go find the equilibrium constant and you could go find your pH, or probably the more practical speaking one in the laboratory is that if you know who the acid is, we will have a value of the equilibrium constant at a certain temperature that we can go just look up in a table. I actually gave you a table. You have one as one of your handouts, a whole list. Oh my gosh, goes on for like 3 pages or so. A listing of all the possible common acids, weak acids that we know about, and some bases, that we have the equilibrium constants. That's going to really be what we're going to be doing, is given the equilibrium constants, go find the concentrations so that we can then go and calculate what the pH is. All right, so let's just take these guys in turn here and talk about the constants first. So that equilibrium constant, they are going to be officially referred to as ionization constants. With salts, remember, when they break up into cations and anions for being strong electrolytes, we'll refer to those technically as dissociation. For acids and bases, they're called ionization because remember, the ionization or the formation of those hydronium ions, it's because that hydrogen ion then is reacting with a solvent molecule of water to get H and H2O going together to make H3O, so plus. So that's why these guys are technically called ionization constants, and then you would have a Ka. All right, so here's a reaction that you're going to get sick of seeing because it's probably one of the most well studied, and so therefore a lot of our problems are going to be dealing with it. So this is acetic acid, CH3COO or CO2. Remember, that's the acetate ion. This is written out in the format that kind of depicts how you draw the Lewis structure. So the acid hydrogen, the acidic hydrogen is just that last one there. Okay, so I put the equilibrium arrow here, and then I just put H plus. Remember, that's really then H3O plus, again, kind of beating that into the ground. Okay, and then there's your acetate ion, but it's reversible, so this is going to have an equilibrium expression. So we call that equilibrium constant, though, we'll forego calling it a Kc, because now we want to just talk about, oh my gosh, for like the next week or two, talk about just acids, bases, and we will do salts, might be after spring break. So we're going to have that be called a Ka value. And you won't have to memorize the Ka for acetic acid. Remember, that's just vinegar. You won't have to memorize it, but I'll bet you after 2 weeks you're going to know it because we do so many problems. 1.8 times 10 to the minus 5. I like to use a little more sig fig, so sometimes I'll use, it's 1.75 times 10 to the negative 5, okay? So you'll see me, we can use 1.8 or you can use 1.75 as well. It's a constant, so it doesn't truly affect too much your sig figs. It's going to be mainly the molarities, okay? So I'm not sure why my little brackets didn't show up down here, but you'll have then your products, set up the equilibrium expression, you got your products then over reactants, and then you got an equilibrium constant. Okay, so that handout I was talking about, you can look at those, and just like we did strengths of acids, you know, like HCl versus HI versus HBr, that, you know, as you go down in a family, then that the strength of the acid increases. You can do the same thing here, and what's really cool is you just simply look at the numbers. The greater the value of the K, the strength of the acid is going to increase. Think about that in terms of the reaction. What you're saying is that if the K value is increasing, well then the numerator is getting bigger, right? That would make this guy get bigger. So you're talking about then the number of ions being greater in solution. That's what makes it a stronger acid, is the higher you can get the concentration of hydrogen ions, hydronium, that's what makes it a strong acid. These guys aren't going to be one-to-one stoichiometry, but it's going to be, you know, approaching that, right? It'll always be approaching it because you'll increase that level. So when I look at my values for some Kas here, I might give you a list and say, hey, put these guys in order of increase or decreasing acidity. Okay, well, so if I put these guys I'm doing from greatest acidity to lowest, HF is going to be the top dog because when you look at his numbers, he had the highest Ka. And then just walk all the other ones down then until finally you get down to HCN, poor little guy, 10 to the minus 10th. Very, very low acidity, hardly any hydrogen ions splitting from that cyanide ion, okay? Remember how that you can talk about the strengths of the acids, and then analogously to that, you can talk about then the strength of their conjugates. So if HF, out of these set, if HF is the strongest acid, well then he's got the weakest conjugate base. In other words, in order to get that, to combine again with that proton and turn back into HF, less likely. You're going to have increasing strength. So it's whoever is the weakest of the acids has the strongest of the conjugate bases, and vice versa. That's stuff that we had talked about in a previous, we were actually in class together for that. Okay, so calculations, like I was saying before, What if you are given the concentrations and your goal is to find the K? And then we'll do the other ones later, which will really be the ones we spend the most time on. Given the K, now go try to find the concentrations. Okay, just like we did with the molality calculations, you can find the concentrations, you can find the percent ionization, we'll find the Ks, and the percent ionization then is really telling you to what degree that acid was ionizing. What is its strength? It's not going to be 100%, but what percentage is it? So just gave you a general formula here that you can kind of think about. The percent ionization, to what degree that weak acid ionized. Find out then, what is its hydrogen ion concentration at equilibrium, that's what the little abbreviation EQ there is, divided by HA with a little subscript of 0. That is actually technically pronounced naught. It's an old English or British thing. You guys may have heard about it in math class. Oops, that's supposed to be an H. It's called naught, so we call it HA naught, and then the concentration. Whatever the original concentration of your acid is, you would find your equilibrium concentration of hydrogen ions compared to the initial concentration of the acid times 100. That's going to give you then your percent ionization. HA is going to be just a generic way of indicating that I had a monoprotic acid, just one proton that would be involved in the dissociation or the ionization, okay? So we'll put A because a lot of times we don't want to specify a particular acid. We just want to say, hey, you've got a monoprotic acid, you're going to have one ion in solution. So like this first problem we're going to do here, you're going to have your hydrogen ion, and then you're going to have whoever his conjugate is. You know, I mean, is it acetate, anion? Is it going to be the nitrite? Is it a phosphate? I mean, whatever. You're just going to use A for a generic term for anion. So you'll see that 1,000 times, okay? All right, so what if we had A, this first problem here, 0.12 solution, weak, monoprotic, so we'll just set it up in an equilibrium expression as being HA, and they're going to tell us that it's 5% ionized. Find the Ka. So they're telling us to what degree it's ionized. Indirectly, they're telling us the concentrations at equilibrium. Once equilibrium has been established, they're telling us those concentrations, and so we're going to go and then find out the equilibrium constant. Okay, so there's my equilibrium expression. You always want to start off by writing the expression because we're going to be setting up ice tables just like we did for equilibriums here. Not for this one, but we will be, so you always write your expression first. The fact that they've told us that it's 5% ionized at equilibrium then, okay, well then that's what this is. 5% of, meaning multiplication, a 0.12 molar solution. Just take that. This then is going to be the molarity of the hydrogen ion concentration, hydronium, at equilibrium. Okay, well, these guys are in 1-to-1 stoichiometry, so that means if I had 5% ionization for that ion, I'm going to have 5% ionization, or that would be for the anion concentration, and so he'll have this concentration. That means then that if it's only 5% ionized, well then 95% is still in neutral molecular form, unionized form. So that's going to be then the equilibrium concentration then of my acid, still present in solution. Set up your value for your equilibrium constant, specifically labeling it now as a Ka, plug and chug, and then you get an equilibrium constant for that particular acid. Okay, let's do it for then where we're going to find what the ionization constant is. Ionization constant, fancy way of saying equilibrium constant for an acid or a base. So this time though, they're going to give us the values of the concentrations in a different way. But still, the idea here is that we are going to be able to get the equilibrium concentrations, and the goal is to find the equilibrium constant. So here they're going to say the pH of a solution of an acid, and they gave us the concentration. They're going to tell us what the pH is. See, what they're telling us is that they're now giving us what, indirectly, they're giving us what that hydronium ion concentration is at equilibrium. Because if the pH is 2.97, plug it into that expression where you can then back it out and get your hydronium. They're telling us then at equilibrium, well then that's the hydronium ion concentration. So I write my little equation. This is a monoprotic acid, so it's just HA. Have him do his little dissociation, and then voila, that is the equilibrium concentration of the hydronium ion. These guys are 1-to-1 stoichiometry, so that also then is going to be the anion equilibrium concentration. Okay, setting up my little ice table, well, the initial concentration of the acid was 0.1, and then of course I'd have zeros for those two, and then here I have the equilibrium concentrations. Well, then guess what? That's to what degree they changed by. That's how much was produced, so positive values for those. Well, then that's going to be how much was consumed, or how much ended up being taken away from the original concentration. So 0.1 minus that value then is what's going to remain as my equilibrium concentration of my acid. Plug all those guys then, the equilibrium ones, concentrations, go into the formula, and there's my ionization constant, aka my equilibrium constant. Okay. Now, I just threw this in here just for, to show how that you can sort of prove what degree of ionization you have, figure out the percent ionization. So you take the equilibrium concentration of your hydrogen ion divided by the initial. So it's the part out of the whole. Get it? It's still percent. Part out of the whole. What part ended up being an ion form out of what was available totally? You'll then figure out, boy, that really was indeed a pretty weak acid. It was only 0.012% ionized. Okay, so now we want to go then the other direction. Now, given the equilibrium constant. And for homework problems, just be careful. Sometimes I'll put the equilibrium constant right there in the problem for you, and that's how it will be done on an exam and the final as well. But sometimes I want you to read a problem and have to figure out on your own, oh, well, hey, if I have to find out the concentrations, I have to know what the equilibrium constant is. So want you guys to have to figure out that you have to go look it up. And that handout that I gave you of ionization constants, it has more of them than what's given to you in the book. That has every ionization constant, every equilibrium constant that you could ever need for any of the homework problems. So just keep that handy when you're working these guys out, okay? So this is a scenario where when we read the problem, we're going to know, or we'll know that we have to look up the equilibrium constant, because what we're being asked to do is to figure out the concentrations of the species or the percent ionization, okay? Now, that's what we were doing in the previous problem, is figuring out the concentrations, the percent ionization, but they told us what those values were going to be, and we were to find out the K. Now it's just the opposite. Given the K, we're going to go and find out those concentrations. So let's take this guy. Calculate the concentration of all species in solution. Very much want to be always visualizing in our minds, what are all the different chemicals that are in the solution? Who's an ion? Who's a neutral molecule? How much has been ionized? Want to keep that kind of stuff in mind as we go. Okay, this says 0.15 molar acetic acid. So this is, I go look up the K. Again, it's going to be one that you're going to see so often you'll have it memorized, at 25 degrees Celsius. And then part B, calculate the percent ionization. Okay, so our little ionization here, if you want to go strict, I kind of added this as an afterthought, go strict Bronsted-Lowry, where you have the acid as the proton donor. So there's my equilibrium expression. You can just write, like I did previously, H plus going to acetate, and then you just have the acid here. Okay, so either way, it doesn't matter. He's a liquid, so he's not going to be included in any data anyways, okay, because he's a liquid, so he's not going to be found in the equilibrium expression. Okay, so set up your ice table. You have your initial concentration of your acid. At the beginning of the reaction, you got none. You have nothing for the two ions, okay? But then the reaction proceeds to equilibrium, so you would have then produced X amount of your two ions. You would have consumed X amount then of the original acid undergoing the ionization. And so then your equilibrium concentration, 0 plus X is X, 0 plus X is X, 0.15 plus negative X then is 0.15x. So always remember, you're taking these guys and adding them together, and that gives you the equilibrium expression. That's why it's important to know who's being used up, negative, and who's being produced, positive. Okay, so now take those and plug those into the expression. So I write my expression first, then I plug in my values, got my variables, and then it's set equal to the equilibrium constant. Now, as we did with those calculations in the chemical equilibrium chapter, sometimes you'll have squared terms in the numerator and the bottom, and so you just take the square root of it. Or, like that one that was in the previous video, you have that where you have to use the quadratic formula. We're going to cheat. Okay, here we're going to have this x squared term up top, okay? And then we're going to have a binomial on the bottom, so that's going to turn this into something that you would plug into the quadratic formula. in order to solve for x. We're going to cheat. A lot of the acids, of course, that we're using, they're weak, right? These guys are very, very weak, okay? So what you can do is just check your exponent on your K value, and a nice little handy-dandy thing is that if the K value is less than 10 to the minus 3, that's sort of the cutoff. Your book kind of shaves a little bit and says maybe go 10 to the negative 2. So I think that's really too big. 10 to the negative 2 is too large. Go as small as 10 to the negative 3. That's smaller than 10 to the negative 2, right? If your K value is less than 10 to the negative 3 power, guess what? When you do the quadratic formula, what you're going to figure out is that the value of x is going to end up being so small that when you subtract it from your initial concentration, 0.15, in terms of just rounding off to sig figs, it's going to be inconsequential. Whatever that difference is, it would be greater than 2 decimal places or 3 decimal places of difference. So in comparison to the magnitude of 0.15, this value of x that we solve for is going to be so small that essentially all you're going to end up plugging into the calculator anyways is just the original 0.15. Haha, so what this is going to do, it's going to simplify these binomials to being just simply a number. So now it's going to be essentially x squared divided by 0.15 and then equal to your equilibrium constant. That greatly reduces the algebra for us down to real simple terms. So go through and do the rest of the arithmetic here, and you'll have then your value of x. Okay, you got to take the square root, right? You'll take square root of both sides, ignoring a negative solution, right? That makes no sense, okay? That your value for x, which then is your values of your equilibrium concentrations of the two ions, right? Those are both going to be x's up here, okay? That those concentrations then are going to be the 1.6 times 10 to the minus 3. And that was the first idea thing is figure out what the concentrations are. Well, those are the two ions. How much then is still in the form of the original neutral acid? So just plug in the value of x. Notice that x value, even by doing the assumption, that x value, that concentration is so minimal that when you do the subtraction, within sig figs, rounding off to 2 decimal places, your concentration of your original acid still essentially is the same. How could you prove that? Really by figuring out the percent ionization. So take that hydrogen ion concentration divided by the initial times 100. Yes, you're only going to have then 1.1%. So that little assumption that we made, that if your K is less than 10 to the negative 3, that you can go ahead and simplify those binomial expressions. You can literally just drop the x out and leave it with just the number, okay? You can always calculate the percent ionization, and if the percent ionization comes out to be less than 5%, you know then that your assumption, doing that simplification of the binomials, it means that you were good to go on making an assumption for that binomial to simplify. If your percent ionization comes out to be 5% or greater, then you have to go back and leave that binomial put, and you've got to do the quadratic formula then. You'll have to crank out the algebra and have it in the form of ax squared plus bx plus c equals 0, and then plug in your quadratic formula if it comes out to be greater than 5%. So it's kind of like a little double check, and we'll do that for different problems. We'll do a little double check to make sure that it's set up properly. Okay, let's do another one. Calculate the concentrations of all species now. Let's do a 0.15. I'm on a 0.15 kick of hydrogen cyanide or hydrocyanic acid. And then here's the K value. So here, this time I just gave it to us again as a part of the problem. Sometimes in homework problems, you have to go get it yourself, okay? Notice it's going to start to be repetitive here because the setup is the same. You're going to have your little ice table there. You'll have your initial concentration. You have 0 of your 2 ions that they ionize into, which is always going to be the hydronium plus whoever the conjugate base is. Okay, you're just breaking the acid apart. Okay, so you'll get then X amount being produced for each of those. So then their equilibrium concentrations will be X amount. That's the unknown. You'll consume, so negative. You'll have consumed X amount, and so then your concentration is whatever the original is, then minus X. Plug those into your equilibrium expression, so always show the setup for the equilibrium expression. Plug those values in, okay? Value of the K is less than 10 to the negative 5. Boy, was it less than 10 to the negative 5, right? So this 0.15 minus x is just going to simplify, or will be approximated. It's an approximation. Is approximated to just simply be 0.15. Okay, so then you simplify your expression to this. Crank it out. Okay, so x squared, take square root. I'll let you do the math. Okay, take square root, throw out the negative solution. Hydrogen and cyanide concentration then 7.7 times 10 to the minus 6. So first thing is calculate the concentrations of all the species in solution. Those are the two ions. Plug it in. Notice, boy, 10 to the negative 6, really, really super small, right? We're really just basically proving that our assumption is okay, and so your original concentration is still going to essentially be 0.15. Why? Double check what that percent ionization was. We were totally in line by doing that assumption, you know, breaking that polynomial down just to be 0.15 because, and dropping the x, because the percent ionization, hydrogen cyanide or hydrocyanic acid, 0.0051%. At least for this 0.15 molar solution, your percent ionization then is going to be very, very small, okay? You may or may not remember that the more dilute the solution is, the more the ionization is. So it's sort of like an opposite effect. The more dilute, you get a higher concentration. But, of course, here it's based on the identity. It's also based on the identity of the acid. So this is because this is hydrogen cyanide who has that particular K value. But we could do the math nonetheless and prove it to ourselves. Okay, now that's for the acids. Now let's just show how that you do the same thing. This is for bases though, all right? Well, so now you're going to be looking up KBs, all right? So here again, what's kind of nice is acetic acid and ammonia are the two most well-studied acids and bases, and lo and behold, their K values are the same. So 1.8 or 1.75, you'll see me use sometimes, 1.75 times 10 to the negative 5. They're both on the same order of ionization. It's only about 4 out of every 1,000 molecules that actually ionize. So depending on what the concentration is, that'll change your percentage ionization. But nonetheless, we can do the same thing. So remember your Bronsted-Lowry reaction. So this is NH3 being put into water. So he's the base. He's the proton acceptor. Remember, he's got that lone pair of electrons. Water, of course, then remember, amphoteric. He'll just do whatever the other guy wants him to do. So water will be the acid and donate the proton. So that's going to give you the ammonium ion. And then when the water loses his proton, that's going to leave you then with hydroxide. Notice how you set up your ice table, though. It's exactly the same thing. Here's the initial concentration of the base, 0 of each of the two ions. You're going to be producing X amount, so X is going to be the equilibrium concentrations of the two ions. You'll be using up X amount of your base, and so then 0.15 minus X will be your amount at equilibrium. Now this is a KB expression. Okay, plug in your values. There again, there's our K value, less than 10 to the negative 3. So this 0.15 minus X can just be under the assumption that it'll be 0.15. Whoop, that should be a 1. 0.15. Do the algebra. So your ammonium and your hydroxide ion concentrations will be 1.6 times 10 to the minus 3. Do the 0.15 minus x, and you essentially end up still getting the 0.15, right? This guy's 10 to the minus 3. And then calculate your percent ionization. I'll let you do that on your own, but you should be able to confirm that you get 1.1% ionization. You're just simply taking this ion concentration, dividing it by the initial concentration, 0.15 times 100, and you get 1.1% ionization. See how you just do it exactly the same way as you do the bases. The equilibrium reaction is really the only thing that looks a little bit different, okay? That will be important if we want to go and find the pHs, because we'll have to then pay particular attention. What color should I use to really bring this guy out? You'll want to pay attention in the equilibrium expression. What ion are you really forming? If you're doing a weak acid, then hopefully it's obvious. You would then have that guy have ionized into hydrogen ions. But notice these Bronsted-Lowry reactions with the bases, that what you end up having produced in solution, and hopefully it's not that big of a leap of knowledge here, that if it's a base, it's a hydroxide ion that's being produced in solution. So if you're finding the pH, well, that's negative log of the hydronium concentration, not the hydroxide ion concentration. Ha-ha! So that's where we have to do a little finagling in order to figure out the solution. So why don't we look at a scenario just like this? So this time they're going to give us the pH of an aqueous solution of ammonia is 11.37. We're going to be asked then to calculate the concentration of the original NH3. Just an added twist, just a little twist on this, okay? But incorporating some of these pH formulas in there now, okay? All right, so they told us that the pH is the 11.37. Now, you don't have to do it exactly this way. You can use those different formulas. You can finagle this in multiple ways. The way that I'm doing it here is I'm using that relationship that the pH sums with the pOH to give 14. So when I plug in my pH of 11.37, I solve for the pOH, it's 2.63. Use that relationship that 10 to the negative of the pH can back it out and give me what my hydroxide ion concentration is. The reason why I need the hydroxide ion concentration is because that's the equilibrium concentration of the hydroxide ion. I just used the same base as what we just did, so this is the same chemical equation. This is our same equilibrium expression. But see, notice now what they're asking us to find is the original concentration. That's the X, the original concentration of the ammonia in the initial line. What information they've given me by telling me what the pH of the solution was at equilibrium is that they were giving me the hydroxide ion solution concentration. So if I'm starting at 0 and I ended up with 2.3, well, then you're taking equilibrium minus I is equal to your C, okay? Because remember, I plus C is going to be your equilibrium concentration, okay? Well, these guys then, 1-to-1 stoichiometry, so whatever that concentration at equilibrium is, that would be the ammonium ion concentration. Heat changes by the same amount. So I'm producing this molarity amount of each of these guys. Well, that means then that over here, I'm consuming that amount. Well, so if I'm starting with X amount, I don't know, that then is going to be X minus that amount then for my equilibrium concentration. Plug it into the equilibrium expression. So those two, the products, those were actually numbers that I was plugging in. Here's my silly little binomial, okay? But my K value is going to be less than 10 to the negative 3. Well, now notice how that this binomial is being simplified is that I'm dropping the 2.3 times 10 to the negative 3 and reducing that down to X, so that I'm going to have an X in the bottom, in the denominator. Why is that being, I'm dropping the 2.3 times 10 to the minus 3? Remember, what we're solving for is the original concentration. The amount that was actually ionized, that thing that we were taking the, X minus, or the concentration minus, that piece of it, that's what is so small. That's why we were taking 0.15 minus X and dropping the X. That X amount that was ionized was so small. Here, we can't throw away the X because that's what we're solving for. That's the initial concentration. Remember, that X is going to be much greater than that amount that was ionized, which is the 2.3 times 10 to the minus 3 molarity. So that's going to just simplify to an X on the bottom. Well, luckily, we need that, right? That's the only X that we're going to end up solving for. There it is, 0.30. My gosh, that is much larger than 2.3 times 10 to the minus 3, the amount that was actually ionized. So that is going to be then the initial concentration of the ammonia solution was 0.30. All right? Okay, so last but not least, and this last section here, this is going to simply be a bonus type situation. For the sake of time, I'm going to not put this, or I may put it as a bonus question or whatever, but this is not going to be required and you won't have to necessarily know how to do the calculations. You need to understand the concept of what's going on, but in order to do the calculations, you're not going to have to do this. In fact, I've scanned everything filled out, but what I'm going to basically just do here is talk about the concepts, the conceptual understanding behind it, and then the math of it, which is on the next page, is just going to be left to be potentially a bonus type of a question then, okay, on your exam. Not exam 2, this would be all for exam 3, okay? What if you had not just a monoprotic, but what if you had a polyprotic? And this includes diprotic. What if it's, H2 something, H2SO4, H2SO3? What if it was H3PO4, so polyprotic, okay? I give you an example here where I've got arsenic acid, okay? So that's going to have H 3ASO4. So I have 3 protons in that acid. So producing the acid, he's supposed to generate those protons, but he's not one of the 7 strong acids, which means that I'm going to have then an equilibrium reaction for the dissociation or for the ionization of these guys. The thing about these polyprotic acids, though, because they're all weak, okay, or for the weak polyprotic acids, is that you don't have all of the protons ionizing at the same time. They each of those protons has their own ionization constant. They have their own equilibrium. So when I pull off the first of the hydrogen ions, okay, I am left then with his conjugate base, which is now going to be H2ASO4 minus 1. Remember when we first did conjugate acids and conjugate bases, and I said, or we practiced how, hey, if you have a species and you want to find the conjugate acid or you want to find the conjugate base, is that you only do one proton at a time. You either added one or took one away, okay? So taking one proton away, this would be then his conjugate base. See how he has then his own unique equilibrium constant. That conjugate base ion then, okay, is much more reluctant. See how that Ka has jumped really, really small, a factor of 10 to the 4th, right, smaller? He's much more reluctant because he's got a negative charge. He would much rather act as a base, right? Somebody that wants to get a proton back. That ionization then of the second proton to then form his now conjugate base, getting a little bit of weaker action on that. And then finally, last but not least, take the third proton off, and you'll then get all the way down to the final form of just the polyatomic ion, and then really, really super weak. Now you're down to 10 to the minus 13th, okay? Well, because you see what great magnitude of differences there are for the ionization of the second or the third or the fourth or whatever protons coming off these polyprotics, the really truly important equilibrium process then, reaction, is really just the first one. To what degree are you even going to get the first proton to ionize? Well, so the general rule of thumb then is that by using just only that first equilibrium, double check just to make sure that it is at least a factor of 10 to the 3rd greater. We're good to go here, because going from 4 to 8, minus 4 to minus 8, okay, there's a factor of 10,000, 10 to the 4th. So where A-OK is that you really only have to consider just the ionization of the first proton, and you don't have to do anything about any of the other two. This is why this is going to be bonus, is that you could actually go through and calculate successively what each equilibrium reaction is going to do and figure out the concentrations of all the ions. Remember, these are all equilibrium reactions, so guess what? All of those ions, you could add up all the hydrogen ions, but all of those ions are in the solution simultaneously, all at once. The only one that really ends up mattering, okay, if our K's align properly, being 1,000 times K1, Ka1 is 1,000 times greater than Ka2. As long as that's set, the only equilibrium that's important is really the first one, but you could go and calculate then the concentrations of all those ions in this series of sequential successive ionization reactions, okay? So that's why it's going to be bonus, but got a little bit of some algebraic manipulations that makes this real simple. If you wanted to go and calculate the concentration of the dianion, get it? The dianion, that was the one that gets formed, the conjugate base that gets formed in the second equilibrium, the dianion, so the HASO4 ion, okay? What's nice is that when you go and do the math, and I show all the algebra on this next page, when you go and do it, you figure out, oh my gosh, it's just simply equal to the second ionization constant, okay? If you want to go all the way, and that would work if you had just a diprotic acid, okay, now my guy's a triprotic, right, but you want to go all the way and then find out what the trianion is, if that's as far as you go. So in other words, I want to find out the concentration going all the way down to the arsenate anion. It's a little bit funkier, but it essentially approximates then taking the second and the third ionization constants multiplied, and then dividing it by whatever the hydronium concentration came out to be by doing the first equilibrium reaction. So those calculations we just got through doing where we solve for X, what was the hydronium concentration at equilibrium, that's what that means, is that that's the hydronium ion concentration that you would have calculated in just the first equilibrium ice table, okay? You calculate that, you really don't even have to go through and do all the other calculations. You're just going to simply do this little cheat, and you could figure out the concentration then of that trianion, okay? It works for all diprotic and all triprotic acids. This one was a triprotic, but it works for the diprotic and the triprotic, so you could use those two formulas. Okay, so I'm just going to show you the next page here, but we're not going to do it because it's only going to be just for bonus. So here's the calculate the concentration. I got a 0.1 molar solution of the arsenic acid, okay? So there's the first equilibrium process where I'm doing the ionization of just one proton, and then I'm left with his conjugate. Let me use a different color, okay? So you set up your ice table. So this is a Ka1. There's what his constant is. You've set up all your stuff, blah, 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 do your algebra, okay? Now you'll notice I left that 0.10 minus x alone. You'll see that I left that alone. This 10 to the minus fourth, gosh, that's awfully close. So I just wanted to be careful with you and wanted to just go ahead and leave that binomial alone. So you'll see that I did indeed end up with a pure quadratic equation. I used the quadratic formula then to solve for x, and that's going to be my hydrogen ion concentration from the first reaction, first equilibrium, plus then the conjugate base there. And then see how that I'm proving it, why I wanted to be careful, why that guy, by being 10 to the minus fourth, was just a little bit too close. You know, the cutoff is 10 to the negative 3. You typically aren't going to have to worry about this, but I wanted to just prove to you, hey, why didn't I just do the assumption and just keep that as 0.100 and drop the x value? It's because when you go back and do the percent ionization, it's 4.88%. That is, you know, to 1 sig fig, that is 5%. So for this one, I picked a borderline guy here. I did want to go and just use the traditional quadratic formula. So I did not simplify the binomial. I had to go through all the algebra. All right, and then there's my concentration of my unionized original arsenic acid. Now the rest of this then, what you'll see me doing is we set up the ice table then now for the second equilibrium reaction, the ionization of the second proton, so pull off the second proton, okay? Notice, excuse me, notice those equilibrium concentrations. My hydronium concentration is not 0. I've already got some that was produced from the first equilibrium reaction. And then notice that the concentration of the dianion then, he's getting plugged in to that side as well. So the only thing that was 0 is then the production of the new conjugate base. X. Now this is going to be 4.88 times 10 to the 3 plus x. You're adding those two together. That guy's just x, and then this guy will be minus. I'm consuming, okay? Plug all that in, set it equal to the Ka2. I left off the rest of all the algebra, just simply went straight shot to the number. And when you do the math, you get that the conjugate base and then the second portion of hydrogen ions that are ionized, that are dissociated or produced, 5.6 times 10 to the minus 8th, ta-da! Just to prove how even doing all the algebra, it does simplify to where you can just simply say that that concentration is going to end up being the Ka2. Last but not least, third equilibrium then. Notice I'm pulling in these concentrations, my hydronium ion concentration, notice I'm taking into account that I had some hydrogen produced from the first equilibrium, plus I've got whatever's produced in the second equilibrium. So I had to add those two together. That's what's there initially, and then 0 of my final trianion. And then there's my concentration that I got out of the calculation for the conjugate base in the previous one, the second equilibrium. X, minus x, do the subtractions, do the additions, plug it into the Ka3, yada, yada, yada. There's my Ka3. I skipped all the algebra, but you get down to then the third portion, or the third concentration of hydrogen ions in solution, plus then the trianion comes out to be this guy. Just to prove to you, do the algebra, it really then could have been approximated or calculated by just using that little shortcut answer there, okay? And so then finally, doing the calculations for all the species in solution, There I have what amount was left over of the original unionized acid. How much in the first equilibrium did I have of the dianion, the monoanion concentration? What was the dianion? What was that final trianion guy? And then total. What was the total hydrogen ion in solution? So I would have the sum of all the H's. Well, notice when you add all those three up, my K2 and K3 were sufficiently greater than 1,000 times less than the K1. The hydrogen ion concentration that I got in the first blasted equilibrium is really the only thing that matters. The H2 and the H3, those numbers were so much smaller in comparison to H plus from the first equilibrium that's really truly just what the equilibrium concentration is. And then thought I would throw in one little caveat, is that just because this is the equilibrium problem for an acid, that remember that when you know the hydrogen ion concentration, coming full circle here, one of the first calculations we did on page 1 is that then you can do the concentration of the hydroxide, okay, because Kw equals the hydrogen ion concentration times the hydroxide ion concentration, and that is equal to the Kw, which is 10 to the minus 14th. So plug in my hydrogen concentration, plug in the K, okay, I just rearranged the equation, right? And then you could solve for the hydroxide ion concentration as well, okay? Just for fun, right there at the end. Okay.